Hi, I'm Younghwan from KAIST, and in this talk, I'll be introducing a sync service we built called Simba, which provides reliable, consistent, and efficient data sync service for mobile apps. This is a joint work with Nitin, Akshat, and Cristian from NEC Labs America. So as you know, there has been a massive growth in mobile data traffic. According to Cisco, amount of mobile data traffic generated will reach about 24.3 exabytes per month by 2019, or 190 exabytes globally by 2018. So how big is that? So this is equivalent to 42 trillion images or 4 trillion video clips. So inevitably, we are seeing an increase of data-centric mobile apps. So what do we mean by data-centric? So data-centric apps manage data locally in their devices, remotely in the cloud, and take care of synchronizing these data between other devices. And most apps nowadays fall into this category. So however, writing high-quality data-centric apps is hard. Developers have to design and implement a bunch of requirements, many of which are crucial for delivering a great mobile experience. Let me explain why this is so hard. So first, data-centric apps need to guarantee reliability at failures. For example, mobile users might experience network disruption in middle of sync. And you might be updating a file and suddenly app dies or device turns off because you threw your phone on the ground or pulled off your battery. So what you end up is corrupted data. Second, apps need to guarantee consistency. For example, how do we maintain a consistency of data when you were working on some file with your smartphone and then move to a different place to work on your tablets? Moreover, let's look at how recent apps like to manage data. A photo album app stores structured metadata in a table, while the unstructured photo data will be stored in the object store. Then how do you provide the sync atomicity of these two interdependent data? And lastly, mobile apps, of course, need to be resource efficient. It must minimize the cellular data usage for billing and reduce battery usage by eliminating any unnecessary network radio usage. So how do we achieve these goals? We have two options. Option one, everyone can implement all of this on their own, building inside their apps. Or option two is to just use the sync services that do it for you. For example, like Dropbox, Google Drive, iCloud are the examples of these sync services. Then let's see how current mobile apps provide reliability at failures. We carried out a test to see how mobile apps recover after failures like network disruption, local app crash, and device power loss. So we tested 15 apps that use tables and updates. Some apps implemented their own sync mechanism, while some used existing sync services like Dropbox, Parse, and Kimby. So here's how we ran the test. We have the first client do the write or update of tabular or object data. Then to simulate the network disruption, we activated the airplane mode. For the crash simulation, we either manually killed the app or pulled the battery out. Then we observed the recovery result at client 1, as well as what the second client sees if the client 1 synced after the recovery. So in summary, we find out that current mobiles are not reliable. So in disruption failure test, we found that apps like Hue, Tumblr, and Facebook lose data if app or notification was closed during the disruption. Some apps like Tomdroid, UPM, and KeyPass to Android didn't even notify the user of a sync failure. And interestingly, if we tried to manually sync during the disruption, Evernote app created multiple copies of the same note. So in case of a crash failure, we found that Instagram and KeyPass to Android created partial object locally without syncing. And more serious problem was found in Dropbox and Evernote, where they ended up corrupting the object, which was synced to the second client. So some important observations we found were that no app in our study was able to recover correctly from crash during the object update. And moreover, many apps that do provide object update feature in the PC version simply disable the object update capability altogether in the mobile version. So if you are interested in more details of the study, you can find that in our paper. All right, so we see that there are so many problems in the current apps, no matter whether they implement their own data management mechanisms or use existing sync services. So what do we do? Let me first list the requirements or goals that a sync as a service should have. First, a sync service should be able to guarantee reliability where the user can always sync to the latest data in the server or cloud. Second, it should guarantee consistency where user always sees data at a consistent state, even after failures. And it should provide atomic synchronizations of interdependent structured table and unstructured object data. And third, it needs to guarantee efficiency where data traffic necessary for sync and recovery is generated at minimal and radio usage is reduced to save the device's battery. Okay, so now let me introduce the design of our solution that achieves these goals. To achieve these goals, we introduced Simba, a reliable, consistent, and efficient data sync service for mobile apps. The key contribution of Simba is that first, it provides a high-level programming abstraction for mobile apps. So basically, Simba provides a CRUD-like API, which is the create, read, update, and delete operations, to mobile apps to support easy app developments. So we selected this interface because this is what most of the existing mobile apps use already. We also make it easy for apps to manage tabular and object data with a unified API as well. Second, Simba provides a data consistency to apps by transparently handling failure detection and data recovery under the hood. It also takes care of sync atomicity between the interdependent tabular and object data. So the takeaway here is that app developers now do not have to worry about anything about the data management for syncs and failures anymore. And lastly, Simba is resource frugal by clustering delay-tolerant messages to reduce number of messages as well as the radio usage. And due to the limited time, I will be mainly talking about the first two designs in this talk. So let me first show you how simple it is to implement an app using Simba. Here is a sample code for a photo app that utilizes Simba as a sync service. So first, tabular object unified table can be created by calling a create table function. So we have the metadata of a photo, name, and then the actual object photo. Now we can register this table to use Simba as a sync service by registering the read and write periods. So what's awesome here is that now the app is done taking care of all these complex syncs and failure management. Simba takes care of all of that. Next, to write or add a new photo, we do this by calling a write data function. So we call the write data function with the name of photo to be Snoopy, and then we simply call a write function to write the data into a buffer. So if we want to retrieve the photo that we added, then we will call the read data function with the name of the photo, which should be the Snoopy again, and then simply call read function to read that object data into a buffer. And lastly, for handling conflict resolutions, we will just call begin CR to lock the table for conflict resolutions, get the conflict roles by calling get conflict roles, and then resolve these conflicts by choosing my versions, their versions, or other ways such as revising at the time of the conflict resolution. So you can see that this is pretty simple for any app developers to use. So now let me explain how Simba sync service is actually run. Here's an overall architecture of Simba. So sync service is done by transferring sync messages between the Simba client and then the Simba cloud. So Simba cloud takes care of managing data sync across multiple client apps and tables by responding to the client's sync requests and pushing the notifications for new or updated data. So, and the Simba's sync protocol is based on the versioning each row with a unique ID. So in this paper, we focus mainly on the workings of the Simba client. So for those of you who are interested in the Simba cloud work, please stay tuned because this will be presented in the EuroSys paper, EuroSys this year. So, okay, so let's now look at the Simba client. Basically, Simba client is a service running inside the client device that takes care of the managing tabular and object data, as well as syncing updates with the Simba cloud. Here are some main components of Simba client. So Simba client API provides the interface for the mobile apps to access the table and object data, and is also responsible for alerting the events such as there's a new data or there's a conflict in a row. Then Simba sync handles all the sync-related operations and handles like fault tolerance, data consistency, row level atomicity, and etc. Then all these sync messages are sent and received via the network manager, which also receives the notifications from the Simba cloud in case of there's a new data. And lastly, the Simba data store provides a unified store for interdependent tabular and object data. So let's ask the question, why do we want this unified store for mobile apps? It's because you wouldn't want the half-formed data to appear on your phone. For example, you wouldn't want an updated photo object appear on your phone while the metadata of that photo is from the previous version. So Simba's data store provides a logically unified table store. This is done by having a physical table store with an object ID that links to an object store that stores the actual object data. So for fine-grained thinking, we further subdivide the object into chunks and store them. Our current implementation uses SQLite for table store and LevelDB for object store, which is the LSM store. So since there existed no object store code for Android, we had to port LevelDB ourselves. Okay, great. So how does Simba actually provide reliability and consistency then? So we do this by introducing number of local states into Simba. These local states determine things like whether the data is synced to the latest version or is it updated and waiting for sync. It also determines whether an object update is completed or ready for sync. And lastly, it determines the status of the data failures and what recovery actions to take with it. Here are some of the local states that Simba uses. So for example, the first two flags, flag TD and flag OD, are the dirty flags that identify whether there was an update in the tabular or object data. Count OO shows the number of opened objects for update. So we identify a row as ready for sync when the value of count OO is 0. Flag SP identifies whether a row is currently sync pending. And lastly, the flag CF identifies that a row resulted in a conflict after the sync. So in addition, we add a persistent dirty chunk table, which contains the IDs of the chunks per object that have been updated. So let me now explain how Simba recovers from the failures. First goal of Simba is to return to a consistent state after the network disruption. For this, Simba consults the current state and server responses such as conflict for table or object or an update for table or an object to detect and recover from the network disruption. So the recovery can take any form of like no operations, normal operations, retry, reset and retry, and move forward. So here are some of the simple examples on how recovery is actually done. So for an upstream sync case, let us consider that there was a network disruption after the sync request message was sent, but before the client received the sync response back from the Simba cloud. So this implies that the client is in a missed response state, which takes the recovery policy of reset and retry. So the recovery action will be to reset all the flags back to the previous version before the sync actually happened, and then restart the sync process. Now for the downstream sync case, let's say that the Simba cloud sent a message to Simba client that there's an update for the object data. But before Simba client could actually receive all these updated object data, we were disconnected. This is a partial response state then. So in this case, we will delete the partial response entry and resend the downstream sync request to the Simba cloud after the reconnection. Now then, how does Simba recover from an app or device crash? So the goal here is to roll back or even forward to a consistent state after the crash. So for this, Simba recovers from crash by consulting the 5 local states that I talked about, the flags and the dirty chunk table. So let me give you some examples of how Simba recovers. First, let's say that a device crashes in the middle of the sync process. So at app restart, the Simba detects that this row was in a sync process by checking the sync pending flag is set to 1. So if it sees that the count OO is set to 0, then we consider that the object was not in the middle of write, so the row is in a consistent state but not synced. So Simba allows the app to restart the sync process by first setting this sync pending flag back to 0 and then start the sync process with the Simba cloud. Now, let's say that a crash occurred while the object was opened for updates. So this means that the object was left open at crash, so the count OO value will be greater than 0. So Simba then identifies whether this object is corrupted or not by checking the dirty flag for the object data. So if the dirty flag is set to 0, it signifies that the object was opened for write, but has not been written yet. So this, we simply restart the upstream sync for the first row case. However, in case the object was dirtied and set the dirty flag to 1, then Simba identifies this row as a torn row and starts the server-assisted recovery by requesting for the consistent row version from the Simba cloud. Then once the recovery is done, it resets all the flags back to 0, and then now we are back to a consistent state. So now that I described about the design of Simba, let's now evaluate how Simba performs in practice. Here we aim to evaluate two things. Does Simba provide transparency to apps? And does Simba perform well for sync and local I/O? For this, we use Simba Client as either Galaxy Nexus or Nexus 7 phones running Android 4.2, and Simba Cloud running on 8 VMs across 2 Intel Xeon servers, each with dual 8-core and 64 GB of DRAM and disks. The networks we used were Wi-Fi, and cellular networks was using 4G LTE. So we first look at how easy it is to develop an app with Simba. Here are some of the apps that we implemented using Simba. So Simba Notes is an Evernote-like app with rich note-taking features. Heartbeat Monitor app records person's health condition like heart rate and syncs to the cloud. Similarly, the Car Sensor app records car's conditions like speed, RPM, and uploads the data to the cloud. And lastly, we also implemented the Photo app we've been talking about with operations like write, update, read, and delete of tabular and object data. So as you can see from the table, the number of lines implemented, so it only required a few hundred lines of code to use Simba for data management and syncs. So you can see it's about 300 lines of code for using Simba. But in reality, most of them were just wrap-up functions. So real data management codes were actually usually implemented in tens of lines of code. And we also tried building a photo app with existing sync service to compare the development efforts. So we picked Dropbox in this case, since it is a popular sync service that provides the API for table stores as well as the object stores. And as we expected, this required a lot of more efforts due to a number of limitations. So let me summarize some of them. So first, Dropbox had separate APIs for tables and files, so resulting in no mechanism to handle atomic operations for these interdependent data. And what's more problematic was that even within the table store, it did not provide the row-level atomicity, but only the column level. And in case of failure handling, Dropbox could not detect the torn rows, and resulting in syncing corrupted data to the server. So we also confirmed that Simba performs comparable to existing sync services. We compared Simba's end-to-end sync performance to Dropbox while syncing a 1-byte column data or 1-byte column and 1 kilobyte object. So for this experiment, we measured the time for one client to write a new data and have client 2 receive the update. The clients were in Korea while Simba Cloud was in Princeton and Dropbox server was in California. And here are the results for syncing over either Wi-Fi networks or 3G networks. So we include the ping time to show the base latency between the client and the server. The y-axis shows the time in milliseconds. So basically, overall, we see that network latency consists only of a small component of the sync latency. And moreover, Simba performs comparable to Dropbox in all cases. Next, we measure how Simba performs in local I/O, such as write, read, and delete compared to Dropbox. For this, we measure the time to do local I/O for a single row that contains 1 megabyte object data. And then the result graph is shown as this. The y-axis shows the time in seconds. So we include the base performance for ext4 and SQLite as a reference. So we find that Simba performs about 10% worse than Dropbox for write and delete, which is mainly due to the IPC overhead from communicating between the Simba app to the Simba client. In case of the delete, Simba performs actually better than Dropbox. This is due to the Simba's lazy deletion policy, where the data is marked for delete, but only deleted after the sync has been completed. So in conclusion, we argued that building a data-centric mobile app should be transparent. App developers' job is to focus on the app call logic, while it is the lower layer sync service that should handle complex network and data management. Therefore, in this paper, we presented a Simba, a reliable, consistent, and efficient data sync service that provides unified Simba table and API for managing tabular and object data. We showed that Simba handles automatic data syncs and failures transparently. And moreover, Simba is resource frugal with delay tolerant crossing of sync messages. And lastly, through evaluation, we showed that Simba is practical for real-world usage. It is easy to develop a Simba app with CRUD-like API, and also the sync and local I/O performance is comparable to the existing sync services. So this is the end of my talk. If you are interested in using our code, Simba source code is currently available at GitHub. And for updated news, please check our project homepage as well. Thank you, and I would like to take any questions. Questions? No questions?
I'll ask one question, which is, so you're handling object and row data. Do you think for mobile devices there's any interest in expanding beyond that for application development and being able to sync? Or do you think or have you seen any need for that?
So are you asking, is there a need for current mobile apps to actually have this interdependent tabular and object data like stored together in a row?
Expanding into different types of data, so more unstructured data or even higher levels of structured data that people might need to use on mobile devices and then also provide the same set of services.
Yes, we believe that there could be some other applications for this. Currently, we were thinking like simple example would be like a photo app where a row has like a tabular data for holding the metadata for the photo, and while the photo data is actually the object that's stored in the object store. But yeah, but we believe that there could be some other application for this as well.
Hi, Nate Rosenblum, EMC Imaginetics. In the APIs you showed, I saw that you register basically for a sync interval on the clients. Does Simba provide any mechanism for doing a sort of callback or push-oriented updates? So if you have one client who's doing modifications and another that is running, will it be notified immediately that there's new data to sync, or is that just done at the standard sync interval?
So you are asking, is there like an event callback from the Simba client to the app? Or
no, from the Simba Cloud to a different client. So if you have two apps on two different devices, one of them is generating mutations to objects. Is the other app notified immediately or just after its sync interval?
Oh, so in the Simba app code example that I showed, so we can actually set the period of the sync. So we could say like, I want to get update notifications every a minute or every like 10 minutes. Then Simba Cloud will notify the clients, like multiple clients, depending on that period. So you get notification then.
Okay, thanks very much.
Right, thank you.
Thank our speaker.